Welcome to Chemistry 112. Well, going where we left off, as I was saying, in the next couple days, I should be introducing a doc cam into here. So it'll be a lot of board, well, essentially math work, but until I'm more familiar with that, we're going to stick with what we got. So sorry if some of the math work is a little harder to read when you're not here. Okay, so mind going to. We last left off, we were talking about vapor pressure and how this was a function of temperature and how also a function of the gas. Like if it's a volatile gas, it's easier to escape. And a non-volatile gas, it's, well, going to hang around a little bit longer. Function of basically the intermolecular forces and temperature. Because remember, like all things, you're fighting, the intermolecular forces are fighting with the kinetic forces to pull the gas apart. Pull the liquid apart into a gas phase. So here's where we get our first major math of the chapter, probably the only major math of this chapter, just assuming it'll load within a reasonable amount of time, but the Clausius Clapeyron equation. This equation setup is going to be similar to an equation we will see later. It's not going to be exactly the same, but it's very similar to one we'll see later. But vapor pressure is directly proportional to temperature because temperature is directly proportional to kinetic energy. So, and it's also indirectly proportional to enthalpy of vaporization. So how much energy does it take to boil it? So we can write an equation that says the natural log of P vaporization. So that ln is our natural log, not the log base 10, but the log base E. Natural log of pressure of vaporization minus equals to the negative enthalpy of vaporization over the gas constant R. Okay, so P vaporization. Okay, so please note the units of R. R is going to be in joules per mole Kelvin, 8.314. When we dealt with gas this last semester, we had what, like 0.08206, which was atmosphere liters, or we had 0.08314, which was bar liters per mole Kelvin. Mostly this semester, we're going to deal with the gas constant R, which is 8.314, which is in joules per mole Kelvin. So we turned a bar liter into a joule. So that's going to cancel out with kilojoules, or the joules essentially of the enthalpy of vaporization. And then 1 over T. So 1 over temperature in Kelvin. Plus ln B, where B, ln beta. Beta is essentially a constant for the liquid, but it's a little bit hard to deal with. So what we actually do is we essentially draw a straight line through two data points. You take a temperature and a vapor pressure, and you draw a straight line, and what you get is the ln beta drops out. And so if we remeasure that, we can get the essentially natural log P vaporization 1 over P vaporization 2. The enthalpy of vaporization over R is 1 over T2 minus 1 over T1. Please note the subscripts, the 2 and the 1. This went from negative to positive because we went, instead of T1 minus T2, we're taking T2 minus T1. How did we get that? Real quick, how did we get that? Just showing that, remember our rule of logs. A rule of logs states that natural log subtracted from another natural log, the things within the parentheses could be brought in as a fraction. If I have ln of x1 minus ln of x2, I can bring it to ln of x1 over x2. We're going to do a similar thing with our 1 over t. the negative fraction of 1 over T1 and minus the negative fraction of 1 over T2 can be brought out and becomes a positive 1 over T2 minus 1 over T1. That's what we're going to do there, and that's actually going to simplify our equation. As we do this, we're going to actually remove our natural log of beta. Going to bring that out as we combine those two equations together. So what we're doing at this point is taking 2 points on the graph and drawing a straight line. We're going to use this to find one of 5 different things in here. We can use this to look at either pressure, one of 2 pressures, one of 2 temperatures, or the enthalpy of vaporization, depending on which variable we have. We're going to have all other variables as we solve this equation. Please note, if we look at this equation, we got to watch our units. That enthalpy of vaporization is typically in kilojoules, while our gas constant is 8.314 joules per mole Kelvin. If we forget to convert those, that could lead to some problems later on. So let's take a look at an actual practice problem. As I work through these practice problems, you'll see I tend to like to write my equation, define all my variables, plug them in, and then start to evaluate. While you don't always have to do this, this will help avoid problems later on. So reading the problem, if water has a vapor pressure of 23.8 torr at 25 degrees C, what will the vapor pressure be at 0 degrees C if the heat of vaporization is 43.9 kilojoules per mole? So we're using our Clausius Clapeyron equation at this point. So let's start recording some of the values on there. Our first value is pressure of 23.8 torr. So P1 is 23.8. Our temperature is 25 degrees C. Of course, we cannot use Celsius. Otherwise, when we have 0 degrees Celsius and we divide by 0, we're going to have a problem. So we have to turn this into Kelvin. 273 plus 25 is 298 Kelvin. We do not know our second pressure, so P2 is going to be unknown. And our temperature, T2, is 0 degrees Celsius, so adding 273 puts us at 273 degrees Kelvin. We are given the enthalpy of vaporization is 43.9 kilojoules per mole, and our ideal gas constant, R, is 8.314 joules per mole Kelvin. Okay, so that meant looking at our equation, we see that we're going to have P1 over P2, then 1 over T2 minus 1 over T1. Now that's going to become a little bit of an issue here in that we're going to have 1 over a variable. So we could actually swap things up and make our lives a little bit easier. As long as we keep the pressure and temperatures linked together, it doesn't matter which one we call P1 and which one we call T1. Which one we call P1 and T1 and which one we call P2 and T2. As long as we keep them linked together. One thing we'll always have to keep in mind is we need to be able to evaluate for a given equation. This is something I cannot just directly teach you. We have to work it out. This is the math part that is going to make our life a little bit harder. So we're going to start plugging our values in after we've swapped the P1 and T1. I would plug in my values. So ln x over 23.8 equals, I'm going to convert this into joules, 43900 because joules, there's 1,000 joules in 1 kilojoule, all over 8.314. So now that we switch this around, 1 over T2, 298. 1 over T1, 273. I've plugged everything in. Now the trick is to evaluate. If you want to do this slow, that's fine. If you want to do this in parts, that's fine. Not everyone's calculators are amazing, so sometimes you want to take it slow. Start with 1 over 298 minus 1 over 273. That, in fact, gives us a negative number. That is okay. It's a negative, really, really small number. I'm getting negative 0.000307 something, something, something. But I'm going to multiply it by a really big number, 43,900, and then divide by my 8.314. So when I evaluated the entire right side of this equation, I'm getting ln, so x over 23.8 is equal to negative 1.6226. It keeps going, but I'm going to round it there. Don't round too prematurely, or it could screw up your numbers, but I think 4 or 5 decimal places should be sufficient. Okay. As I say, as I work this out, please feel free to work these out with me if you have a calculator. If you ever find you cannot get the numbers I'm getting, please let me know. Even if you're doing this at home, please let me know, and I can try to figure out if you're doing something wrong, if I can help you in any way. At this point, we're kind of at an impasse because we have to get rid of this natural log. So the way we get rid of natural logs is what we call an inverse log. To add an inverse log into here, we have to do an identity property. Whatever we do to the left side, we're also going to do to the right side. So I'm going to raise this whole left side to the inverse log of e exponential. And that's going to kill the inverse log. But to do that, I have to also take e to the negative 1.6. So the inverse log is at least on my calculator, the second EX button. EX. And so I run that, and I get a number that's pretty small. It is 0.19738. And it keeps going, but once again, I'm rounding to the 5th decimal place. And that is x over 23.8 torr. Finally, how do we solve for x? We multiply both sides by 23.8. So doing that, 23.8 gives us the pressure at that would be 4.69768, blah, 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 torr. Now, if you keep in mind sig figs at this point, this guy in pressure is 3 significant figures. So we could probably actually round this to 4.70 torr and be safe. I left all the digits in there and tried to figure it out at the very end. But so 4.70 torr would be the pressure. It's not going to be a quite as nicely linear as you'd like it, but so going from 25 degrees for water to 0 degrees for water, we still generate, even though water should be ice at 0 degrees. Water is still generating a really small vapor pressure. really small vapor pressure. The ice is still, particles of the water are breaking up the ice and going into the gas phase. And that's what we end up seeing. As I said, you miss anything on the board, I try to work us through here. But it's always nice to be able to do this in person and see this step. 4.70. Doing another one. Hypothetically, if a liquid with the heat of vaporization of 50 kilojoules per mole has a vapor pressure of 35 torr at 50 degrees, what temperature would the vapor pressure be? 70 degrees torr. What temperature would the vapor pressure be? 70 torr. So this one's a little bit easier. We're given all the values except a temperature this time. Doesn't really matter which one we call P1 and P2. So we're given 50 kilojoules. 8.314. That doesn't change. But now we have 35 torr at 50 degrees C. I have to turn this into Kelvin. Adding 273 makes this 323. And then 70 torr. What is the temperature? Plugging in. ln 70 over 35 equals 50,000 over 814, 1 over 323 minus 1 over T1. So I've just rewrote my equation so as to, with all the values written out. Said, I know this, we want to be tempted to just skip straight to the plug and chug, but it really helps to write this out. Make sure you're all starting on the same starting point. Make sure you know what you have, because there's going to be a lot of equations that look similar, and there's easy places to trip out. If you don't turn kilojoules into joules, that's an easy place you're going to screw up. Easy place. If you do that, you're going to be, because of the whole natural log thing, it's going to be not as big of and direct of a screw up as you would think. It's not just, oh, I moved the decimal point 3 over. It becomes something, a whole different beast sometimes. So you forgot to turn Celsius to Kelvin. That's a big whoopsie that could play a part down the road. Now, in this case, the x is on the right. We know all the values of our natural log, so we can evaluate. 70 over 35 is the same as 2 over 1. So we can do the natural log of 2. It gives us 0.69314, blah, blah, blah. Once we have the natural log of 2, we can multiply by our r and divide by our delta H. So I'm going to do that before I write this value down. So I'm multiplying by our r because it's on the denominator on the right side, and divide by our delta H because it's on the numerator. This is a really small number, and that is fine. This is one of those things you'll have to get used to, especially this equation, because it's a inverse temperature. 0.115257 equals 1 over 323 minus 1 over T. The next thing, maybe we want to get the 1 over T to the other side. So what do we want to do? 1 over t on this side equals 1 over 323 minus the 0.000115257. So I'm getting the exponent. You could have done it the other way. You could have gone the 323 to the other side and then multiplied by a -1. The big thing is that we're getting the unknown, the variable by itself. We're isolating the variable. That's always what we're doing. We're always isolating the variable one way or the other. There's no set way you have to do it. As long as you know how to isolate the variable, you can get it done. There's no order, which is why this is one of those things that I can't just teach you one thing that's always going to work. You have to know how to isolate a variable on your own. So that plus the 1 over 323, that gives us, so 1 over t is equal to 0.002980719. 719. Now that is 1 over t. So how do we get t? You're going to have to take the inverse. That's going to flip that over. The inverse, 1 over x button or x to the negative first button. It depends on what calculator you have, but you're basically flipping this to get the temperature. So the temperature you get is 335.5. This is one of those things you don't want to round prematurely. If I did that with 0.00298, let's see, 298 gives me pretty much the same number. But if I did 0.0030, I would have got 333. So you start losing some, the more you round, the more you could lose in the sig figs later on. But turning that 335.5 into Celsius, you would get 62.5. 62.5 degrees Celsius to double the pressure. It's not an obvious linear scale here, which is kind of a little hard. We doubled the pressure, but to do that, we just changed the temperature by 12 degrees. We went from 50 to 62, and you see this huge jump. So that's why you can't, you have to really use the equation to get that. Yeah. Now, that, as I said, that's the main math we'll have to see for this chapter. Probably the hardest math you'll have to see. It's one of those really complicated equations. You might see 1 or 2 questions on the homework. You might see like 1 question on the test, but it's not going to be a huge point. This phase diagram is a way more interesting thing to look at and a lot easier to generate questions about. So jumping back a couple slides just to go back to the temperature energy diagram, see if I can. A little bit now. Is it gonna? No, it's not gonna. Oh, wait, it is. So we previously looked at this heating curve that looks at essentially a 2D portion of we're heating this energy input versus temperature of this energy, and you see it plateaus when you see a phase change. So after looking at that, that is done at a uniform pressure. A uniform pressure. So that is just one slice of what we're looking at in this phase diagram. This phase diagram compares temperature to pressure. Temperature to pressure. At a given temperature and a given pressure, it tells us what phase would be the most stable phase that would occur. It's essentially, if you keep this pressure the same and you run this across, you would essentially generate the heating curve that we just saw for the angle that, when we hit this boundary, the melting begins and the energy suddenly, the temperature plateaus as we go from ice solid water phase to liquid water phase. And then we see the temperature go up, hit this point here. It plateaus as we go through heat of vaporization. And then we could keep going, blah, 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 heat up the gas. Well, if I change the pressure, it's going to change this curve so we get a different melting point and a different boiling point. We still get that same plateau where it crosses its boundaries, but we just don't see those plateaus as much. But this looks at how the pressure changes, the pressure and temperature change are most occurring. What is occurring? Now, as I said, you don't quite see the energy of vaporization. When you hit this line, you don't see that same plateau, but it's still occurring. But the idea is if I put a block of ice at 25 degrees at one atmosphere of pressure, what should occur? Well, 25 degrees puts it maybe like here. It should melt because the most stable thing is liquid water. If I lowered the pressure to like 0.001, something like that, what should happen? That block of ice should actually sublimate, boil right away at 25 degrees. Because the most stable form under that pressure is water vapor. So this shows us what phase is most stable for a given liquid at any given pressure temperature compensation. Now there's obviously the boiling, the fusion process line that separates the solid from liquid. There is a vaporization line that separates liquid from vapor. And there is a sublimation line that separates solid from gas. So at pressures below 0.006, ice will start to just boil away rather than melt. It'll just kind of evaporate, go straight from solid to gas. Now we get two major points of interest on here. One of which is called the triple point. It's where those three lines come together. Triple point is a special point under certain conditions, under a very exact condition. All three phases exist simultaneously. Because what you got to remember, when you hit this line right here for ice and water, at 0 degrees under one pressure, ice and water exist at the same time. If there is no heat flow into it, you're going to have ice chunks floating in the water. It's not going to all freeze. It's not going to all melt. To make it all melt, you have to keep putting heat in. To make it all freeze, you have to keep pulling heat out. But at no net heat change, 0 degrees Celsius, not all, they're going to have ice and water at the same time. Well, at this triple point, you're going to have ice, liquid water, and water vapor present at the same time. You're going to have all three states of matter generated and in the region at the same time. It's a point where all three can exist simultaneously. There's another point we'll look at in the next slide, which is the critical point right here, the point where this line stops going up. And that's very special for this. There is a critical pressure and a critical temperature which occurs at the critical point. And so what's going to happen? What's happening is that, as you see here, as the pressure goes up, the boiling point went up. In most cases, boiling points are higher at higher pressures, lower at lower pressures. If you remember here on a mountaintop, if you needed to boil water, you would have to heat it for longer. I mean, if you wanted to sterilize water, you had to heat it for longer because it boils at a lower temperature. So in order to make sure to kill all bacteria, you have to heat it for a longer period of time because it's lower temperature. It boils easier, but you're looking for the 100 degrees to kill the bacteria boiling. But this is also how a pressure cooker works. How do you cook food faster? Well, you generate a higher temperature. How do you generate a higher temperature? By putting these guys under intense pressures. So the water in the food that you're heating with can go up, instead of like 100 degrees, 125, 130. So you can calculate how hot you can get it based on what the pressure is. But in general, as the pressure increases, the gas-liquid transition increases. As gases, essentially, more pressure means you need more kinetic energy to break apart. It's not just the intermolecular forces holding it together, it's the pressure itself pushing it down, keeping those gas particles from escaping. So you need more energy to break away and stay away. But the idea here is that there is a limit to this, trend. There will reach a point, which is the critical point, at which this trend breaks. At this critical pressure and critical temperature, something special happens to the liquid-gas transition, and that we achieve what's called a supercritical fluid. Supercritical fluid is basically a gas that acts like a liquid and a liquid that acts like a gas. What do we know about gases? Gases typically don't interact with things, and they expand to fill all available volume. Well, what do we know about most liquids? They're usually contained within a volume, and they dissolve other things by hydration or solvation. Well, a supercritical fluid is essentially a gas that has the ability to solvate molecules, a gas that can essentially dissolve things. It fills the whole container, it dissolves things, and essentially what you can use this for is a convenient way to remove certain particles. Supercritical fluid is one way they can decaffeinate coffee with, I think, supercritical CO2. It's also one of the ways they can do dry cleaning without using toxic chemicals. Because most of the stains that when you can't get clothes wet, you have to have something that's going to dissolve things. So you push this down CO2 to the point where it can pull off nonpolar oily stains, because it's a very nonpolar gas. It can pull off these oily stains, and then what happens is after it dissolved it, you vent them, and it pulls the stain with it as the gas vents away. This is also, I think, supercritical fluids are often used in circuitry. You're building a silicon chip, you have some debris that you need to get rid of. The supercritical fluid is going to all those debris chip, because we cannot afford to get those chips wet. We can't use just a traditional solvent. It's a really neat thing. Wish I could show you guys more about it, but no, I don't think we're achieving that here. So what will these phase diagrams be used for? Phase diagrams be used for get various easy questions, either like what is the phase at these units, or if I went from this to this transition, what phase would I end up at, or what is the critical point, or what is the triple point, or where do these occur? The only thing you really need to worry about here, one, being able to read these things in the first place, and two, double checking your units. Because temperature could be given in Celsius, it could be given in Kelvin. Pressure could be given in atmospheres or bars or torr or whatever. So just double check your units. So this one's CO2. So note the 0 point is right here. 0 point is right there. So what state of gas would this be at? 10 atmospheres, negative 60 degrees C. So negative 60 is right here. 10 atmospheres, about there. And this scale is actually logarithmic. So it's not like 110, 20. No, that's 100. So 20 would be like, if 10 is bloop, 20 might be like bloop right there. So it's not going to be. So CO2 is a solid if you chill it, if you pressurize it to 10 atmospheres and chill it down to negative 60. At 1,000 atmospheres, so right up here, but 80 degrees C, you can achieve a supercritical fluid. What temperature will dry ice sublime at standard pressure? This one's actually, standard pressure is 1 atmosphere. This one is actually marked off on the graph for you, but blah, blah, blah. Standard pressure, it would sublime at negative 78.5 degrees C. So that is essentially the freezing point of dry ice. So when you hear about like, oh, the Pfizer vaccine needs to be stored, they're using dry ice to store it, they're essentially storing it at negative 78.5 degrees and below. They have to use dry ice. And problem with dry ice is though, unless you have a deep freezer, it's going to boil off. You have to recollect it. Triple point is here, supercritical. This graph is noticeably different from, say, the water one. The water one, you notice that the water one, the graph went one way, it kind of V'd off. This one kind of loops around into kind of a, I don't really know how to describe that shape, but like kind of like a bent fork or something like that. It's that as the pressure goes up, it becomes easier and easier to become a solid. As the other case, with ice, as the pressure went up, it's harder and harder to make it solid. And that has to do with the density, the packing of these molecules. But so each graph is different. You'll have to take it as it comes. And you're just essentially reading the graph. And if you can do that, that should be some easy points. Solid, supercritical fluid. Now, that is the portion of the chapter that has to do with liquids. From now on, we're going to talk about the solids and solid properties. There's not going to be a lot of math about here. There's a little bit of conceptualizing these in 3 dimensions, so we'll work with this, but this kind of hiddenness, this chapter. So we can have 4 major types of solids we're going to discuss. Metallic solids, which is basically all metals. The free-floating sea of electrons. We have ionic solids, which is when we take our metal and non-metal and mix them together, which they share electrons through electrostatic attractions and ionic bonds. And we'll talk about each of these guys individually, so don't worry about too much. Just yet, covalent network solids, which is all non-metals. And because we know non-metals make covalent bonds, they're all going to have a covalently sharing electrons the same way in Lewis structures. It's just going to be a lot bigger Lewis structures. And molecular solids. Molecular solid is just an individual molecule, the covalently bonded molecule that's going to mix with another individual molecule. Like, how does water freeze? Water is a distinct H2O. It's not H20O10. It's two H's, one O. How does two H's, one O bind with another one? How does hexane, which is C6H14, freeze with other hexane? How does CO2 freeze? And these are all, these come back to our strong van der Waals attractions. These are all the intermolecular forces hold these guys together. So this is what happens when the liquids we were mostly talking about last chapter freeze, the molecular solids. Now, when we talk about solids, most of the time we're going to talk about some basic structures. They can adopt two different types, one of which we'll talk about, the other we won't really talk about. The one we'll talk about, which is 90% of the cases, which are an orderly repeating pattern or geometry of atoms, which we call a crystalline solid. So when we're talking about a crystalline solid, we're not necessarily saying like, oh, look at that giant geode over there where you can see cumulus crystals. Just even salt, grains of salt are going to adopt what's called a crystalline solid. It's basically a repeating pattern that's going to make up the structure. If you grew the salt large enough, you might be able to see a giant crystal. But crystalline solids could be, you don't have to physically observe it with your eyes. It's meaning a repeating pattern of atoms, of NaCl, NaCl, NaCl all the way through. The other type is going to be a very disordered pattern, which is amorphous, which means without shape. So it's glass can actually, some old glass types can be like amorphous, where it's like not necessarily a repeating pattern. It's doesn't hold its shape as well. That can kind of melt. It's often like a solid that can act like a liquid at times. The molecules aren't really bound in one position. But crystalline solids have a definite shape. They have a defined melting point. They usually at lower energy and usually more stable because of the order here. So that's why we're typically going to deal with it. If we have an amorphous solid, it's kind of hard to define all these things, so it's not really worth talking about for the few exceptions. But the first thing we will have to recognize is what's called a unit cell. A unit cell is essentially, to describe these guys, we need 3 dimensions. And since these crystalline structures are going to have a repeating geometry, we can break that repeating geometry into the simplest 3D representation, which is called the unit cell. And we can describe this by holding what we call a crystal lattice on it. It's an abstract scaffolding which we use to hang the atoms. Like if I draw a box from this atom to this atom, and this atom to this atom, it's essentially an imaginary box that helps us see where the repetition is. Looking two-dimensionally at this guy up here, this little pattern, you could draw like 4 different unit cells depending on where you put the scaffolding. You could put it at the bottoms of all the diamonds, and if you move that box up, down, left, right, you're going to get the same pattern. You could put it at the center dots of the diamonds, and you move that box up, down, left, right, you're going to get that same box pattern. I could put a diamond through the center box of all the diamonds. If I shift that up, down, wherever, it's going to have that same pattern. Or I could just do the diamond itself. All those would be a repeating pattern that you would see throughout this shape. Now, the 3 most common unit cells we're going to look at are these cubic shapes. We have what's called a simple cubic, a face-centered cubic, and a body-centered cubic. Body-centered cubic will be abbreviated as BCC. Face-centered cubic will be FCC. But these guys will come up a lot. So a simple cubic is you make a cube, so six faces, 8 corners. Each of those 8 corners are linked with 1 atom each. So I'm drawing a box between 4 atoms on top and a box between 4 atoms on bottom. They all line up. Now, when we have a body-centered cubic, we take that same simple cubic, except now there is an atom fully in the center of that box. If I tried to draw this, I couldn't draw a line straight down from this atom to this blue atom. But just note above that, there's going to be a blue atom in the next box up. There's a blue atom in the next box down, and the next box front and back. And face-centered cubic, so you take that same simple cubic, and now we put atoms directly in the face of that box. So it looks like a 5-pip side. It looks like a 5. You have pips in all 4 corners and 1 pip right in the center. The atom is right smack dab in the face of that box. Now, because there's 6 faces of the box, there are 6 face-centered atoms in that cubic. But all of them will start with the basic cubic structure with the atoms in all the corners. Now, we'll start with metallic solids because they're actually going to be one of the easier solids. They will want to pack the best. They're solids consisting only of metals. Now, the bonds are stronger than dispersion forces. So they're better than our London dispersion forces, which are really weak. But they're weaker than what we call covalent bonds. Now, covalent bonds, remember, we shared electron to get to those magic number, the octets. We try to get 8 electrons to fill the s and the p orbitals, the 2s and the 6p to make that 8. Even if we wanted to make covalent bonds, most of the metals don't have enough electrons anyway. Now, because of this, the solids can have low to relatively high melting points depending on how they are. Most of them are reasonably high, but there's a couple exceptions. For example, mercury. Mercury is a liquid at room temperature. So these guys get stabilized by what's called a sea of electrons. We have these d electrons in most of the cases that are able to delocalize from the atom, and they kind of like shift between the atoms, kind of like sharing among them all in order to stabilize them all in turn. They're able to move between the atoms in order to help stabilize everything just a little bit. Now, because these electrons are kind of like floating between them and they're not really stuck in a bond or stuck, localized in a charged atom, these makes most metals very mobile, meaning with the right force, these atoms can be separated, which is why a lot of metals have such neat things, like they are able to be malleable. You take metals, you hammer them, you're going to leave dents in them, you're going to pound them into shapes because the atoms are not stuck in one place. You can cram them closer together or make them smush apart because the atoms are not stuck in one place. Be very ductile. You can draw them out into wires. So you're essentially peeling a layer off and turning it into just a long chain because they're not necessarily stuck in one place. They're able to slip and slide apart because of the sea of electrons. Also, because they are not stuck in one place, they're able to conduct heat. They're able to vibrate against each other and transfer heat very easily. Because the electrons are not stuck in one place, They can conduct electricity very easily. Metals conduct electricity because you have to essentially travel. You're essentially, when you're running a current through it, you have to move electrons through. Electron bump, 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 like a series of bumper cars through the atom. And if the electrons are stuck in one place, you can't really transfer that charge. But in this case, since the electrons are kind of free flowing, electron hits the first guy and you just have like a chain effect that travels through very rapidly. So properties of metals: low to high melting points, but the malleable, they're ductile, they conduct heat and electricity very well. Not very soluble in many liquids. So most of these metals will adopt our three basic shapes: our simple, our body-centered cubic, or face-centered cubic, to get them as close as possible as we can. We're trying to pack them in as close as we can so the atoms can be touching each other and transfer the electrons more easily. The more space between the atoms, the more the electrons would have to transfer, and the harder it would be to transfer. So we want to pack these guys as well as we can. Now, looking at this simple cubic down here, you notice if I did this simple cubic, not all the atom of each atom would fit within a unit cell. The atom is actually sliced into a small fragment. The atom is actually sliced into a small fragment, but that's okay. Because when we count atoms within a unit cell, we're going to add them all up from each fragment. So in a simple cubic, what fragment of a sphere is this guy in the left corner? 1/8. It just, so this is, if I draw cube, then there has to be a fourth cube right there, and then you'd repeat it again on top. So this guy is representing 1/8 of a cube. One of the good things about a corner is how many corners are there in a cube. Should be 8. 4 on the top, 4 on the bottom. So when we look at a simple cubic, each sphere is 1/8, but there are 8 of them. So a simple cubic is representing one whole atom. Now, we could hypothetically, this wouldn't be very good, but we could hypothetically draw a unit cell like this, just like a box, and then just try to draw the atom right in the box. But the problem is where it becomes a lot harder to define where does this corner exist with respect to this atom. And so it's actually much easier to put the corner right in the dead center of the atom, somewhere we know where the nucleus is. But where the electron cloud is, it's a little bit harder to define where this atom is in regards to that box. So it's much easier to put the unit cell in the center of the atom. Now, in a body-centered cubic, looking at this guy right here, you still have the simple cubics, you still have the 8 corners, but now you have one atom crammed right in that body. This time we know where it is because it's touching all the other atoms. So we don't have to worry so much about where the corners are at. We just know the center of this atom is right in the dead center of that cube. Now, because it's dead center, none of this atom is outside of the box. So a body-centered cubic is 100% in the box, but there's only one body. There's only one dead center. So in this case, it is one atom in the body, one atom represented between all 8 corners. So a body-centered cubic looks at 2 atoms within a unit cell, 2 whole atoms. And the face is a little bit harder, but you can see this here. The face, it's slanted right here. It's halfway in and halfway out. So each face counts as half of an atom. But if you look at a cube, how many faces are there on a cube? There should be 6. So in a face-centered cubic, you have top, bottom, left, right, front, back. You have 3 atoms in the face, 1 atom in the body. And so you're looking at a total of 4 atoms in that cube. And the unit cells are essentially going to show how these atoms pack within the crystal, and thus how other atoms can interact with it. This packing has a lot to do with, well, like the density, of course. It's going to have a lot to do with interactions. It's going to have a lot to do with solubility and stability and all that stuff. Now, in our book, in our ebook, I don't think this part is in there, but it's part of the old textbook. But I like this part, so I include this part because essentially this is where how do metals interact with other metals. If it's not just a pure metal, it becomes an alloy. When we have a mixture of one or more metals or non-metal into a metal structure, we get what's called an alloy. And these guys are rather useful. We see these all the time, whether we realize or not. These alloys will fit into several different categories depending on how they pack. There's the substitutional alloy, where a lesser element is uniformly substituted in. We essentially subtract one atom, put a new atom in. It's not a constant thing. It's just here and there. Remember, we have a repeating pattern. So it's just like scattershot. This atom wins the lottery, gets placed there. It's not very common, but it's common enough. Interstitial alloys, where the lesser element fills in the holes. So jumping back a second, you can see there's little gaps here. Like if I put an atom right in the dead center, that empty space in that simple cubic, there's space for a small atom if it's small enough to fit right into that hole. This is typically done by carbon. Heterogeneous alloys, where they're just not mixed at all. There's 2 layers. An intermetallic is just, it becomes a compound. It's like a substitutional, but it's actually a constant thing. So it's not really a true alloy. But I have a couple alloys we see. A Wood's metal, which is mostly bismuth, but you can see there's a bunch of other things in there. Whereas it's good for its low melting point. It's often used in fuse plugs and automatic sprinkler systems. So you have essentially a sprinkler system up in the ceiling. How do you get it to release water when there's a fire? Well, it has a really low melting point. So the hot smoke of the fire goes up, hits the detector, the plug melts. The hot smoke melts the plug, and so all that water pressure just comes dumping out just because of the low melting point of this metal. If you had a regular metal, it would be just fine. It wouldn't melt. But this Wood's metal does just that. Brass. Mostly copper, 33% zinc. It becomes more ductile and will take to polish. So stainless steel, it's mostly iron. It's a good deal carbon and a couple other metals that essentially help it resist corrosion. The carbon gives it its strength. The other metals give it the resistance to corrosion. Plumber solder, which is mostly lead, but a little bit of tin. Useful because it's very low melting point. It's very good for soldering the joints of pipes. They need some of that. And silver, we have sterling silver, which is silver and a little bit of copper, which just brighter surface. But there's also dental amalgam, which is silver, tin, copper, and a little bit of mercury, in that it's soft enough that it could be easily worked into a dental filling. They don't have to take a blacksmith hammer to your tooth to get that to shape, the proper shape. So all these are just example of alloys that we kind of still see. Now we'll look at briefly at ionic solids. Now ionic solids, remember, are ions bound together in a crystalline form. So we still have the same properties of pretty much we've looked at these all last semester. You talk about sodium chloride. The reason we say the formula weight of sodium chloride, or we say the molecular formula, because it's really Na3000, Cl3000. It's a repeating thing of sodiums and chlorides. And we abbreviate it as Na1Cl1 because it's a constant pattern. Now, ionic solids have a very high melting point. But due to the localized electrons, they're all stuck in cation-anion pairs. They become very brittle and they don't conduct electricity. So you take a salt block, hit it with a hammer, it doesn't smush, it shatters. Because the electrons are all stuck in one place. They don't allow the atoms. When you hit it and you break the bond, you're breaking along a fault and it's just shattering off. It's not smushing to somewhere else. Now, of course, remember, because of this, most ionic solids are soluble in water. They will dissolve. And once they do dissolve, they can conduct electricity. But because of these ionic interactions, there's a lot of repulsion. So we cannot keep a standard closed packed shape. Atoms cannot touch, the cations can't touch other cations. The anions can't touch other anions. So we're going to have a way for the cations and the anions to separate each other. So what's going to happen is that one ion will adopt your basic shape, your simple cubic, your body-centered cubic, your face-centered cubic. But the other atom will be smushed in there in a different place so as to keep the cations away from the other cations. So there's no cation touching another cation. So we'll have to kind of look at this and try to reason out where the other guy is based on context clues and looking at the shape. But please note the number of cations and the number of anions in the formula will give you, in the unit cell, will be the same formula ratio present in the overall molecule. So if I see 6 sodiums, I should see 6 chlorides. If I see 1 zinc, I should see 2 chlorides. Good. So here's just various examples of different things adopting. Cesium chloride, as you see here, cesium adopts the simple cubic, which is 8 corners, so 1 atom whole, and chloride right in the body, 1 atom whole. So 1 atom total in between all the corners and 1 atom in the body, a 1-to-1 ratio. I can actually show you this one later. I have actually model of this one, sodium chloride. So chloride adopts the face-centered cubic shape. So atom, 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 all those. So chloride, remember, face-centered cubic, 1 from the corners, 3 from the body, puts us at 4 chlorides. The sodium adopts edge and body. Edge and body. So 1 from the body, and how many from the edges? Well, if faces were 50, corners were 1/8, how much of an atom is in the edge? So you got to if I put a box right next to it, and I put a box right above it, How many boxes are touching this edge? We should have box there, box there, box there, box there. So 4 edges are 1/4. How many edges are in a cube? Well, we got to count here. 1, 2, 3, 4. That's 1 atom. 1, 2, 3, 4. That's 2 atoms. 1, 2, 3, 4. 12 edges means there's 3 from the edge, 1 from the body. So this has 4 sodiums, 4 chlorides, which simplifies to NaCl. Na1Cl1. Now that's a really hard one. Sodium fluoride adopts pretty much the same type configuration. But here's a couple really wonky ones. Zinc selenide, which is also referred to as zinc blend, is a common shape that will come up. I think the zinc is in the corners, but it's also in the faces. So face, 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 there. So zinc has 4 atoms. Now the sulfur, zinc sulfide is a little bit harder to tell, but if I tell you this is in the corner and this is in the face, this is in a face and this is in a face, where must this guy be? If I draw a 2-line, if that is on the outmost edge and that is in a corner, that can only be somewhere 100% in that body. So this has a face-centered cubic with 4 atoms. And the sulfur has 4 atoms all in the body. They're not in this dead center, but they're fully within the cell. You kind of have to really look at it really carefully, but they're all fully within the cell. They're in the corners, but they're 100% in the cell. So 4 atoms on zinc, 4 atoms on sulfur makes a 1-to-1 ratio. 4 atoms on zinc, 4 atoms on sulfur, 1-to-1 ratio. This one, magnesium fluoride. This is a very funky shape. Come on. Oh, come on. A very funky shape. Magnesium fluoride. 1, 2, this is kind of a rectangular prism, not full cube. But 1, 2, 3, 1 from the one from the corners, 1 from the body. Magnesium has 2 atoms. Now these fluorides are kind of a little hard to tell, but they are actually in the face up here. Those are you can kind of see it there, kind of harder to see it here with the way this shape is. But these guys are in the face and these 2 guys are in the body. So 1, 2, those 2 add to 3, those 2 add to 4. So magnesium has 2 magnesiums for 4 fluorines, which simplifies at a 1-to-2 ratio. And scandium trifluoride, you'll see scandium's just in the corners and fluoride is in the edges. Edges, remember we said 3. Corners, we said 1. So scandium is a 1-to-3 ratio. So as I said, those are a little bit harder to see. So what might you be expected to do with these later is if I gave you a shape, what is the ratio for that molecular formula? You might have to look at it. You might have to ponder about this a little bit, but it should be an easily reducible ratio of 1-to-1, 1-to-2, 1-to-3, 2-to-3, something like that. But that is where we're stopping for now. I'm not going to get into the molecular solids just yet. But we will see this zinc selenide blend in a next class when we talk about, when we see diamond. But we're almost done. We only have, three slides and a practice problem left. So we are essentially, for all intents and purposes, almost done. And we'll finish up on Tuesday.